Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to week 2 of this course, and just to remind you what we did in week 1 is we started with this model of a small device and in terms of how to understand the current flow through it, and we introduced this concept of a density of states that tells you that in a given energy range, how many states do you have per unit energy for electrons to conduct. And as we discussed, current flow depends on electrons going from left to right, making use of these energy channels that are available. And current flows only in the small energy window between the two electrochemical potentials, because this is the range of energies where one contact wants to fill up these levels, the other one wants to empty them, and so electrons keep flowing. And based on this viewpoint, we first obtained an expression for the conductance, which looked like Q squared D divided by 2T, where D is the density of states in this energy level of interest, and T is the time it takes for an electron to get through. And then we said, well, if you have a ballistic conductor where electrons go straight through, then you can write this time as length divided by the velocity, the average velocity. And based on that, we obtained an expression for the ballistic conductance. And I have these 3 things here because that's an average velocity, and the actual average sort of depends on whether we are talking of a one-dimensional conductor or a two-dimensional conductor or a three-dimensional conductor. And this averaging is discussed in one of the tutorials that go with week 1. Now, similarly, in the diffusive regime, where people think in terms of a conductivity, what we showed was you can obtain this expression for conductivity, which depends on this diffusion coefficient. And here again, there are 3 numbers because this involves an average of V squared. And in 1D, 2D, and 3D, the numbers are different. So it's V squared tau divided by the number of dimensions. That's 1/2 and 1/3. And then this is the density of states. And in 1 dimension is the density of states per unit length. In 2 dimensions is density of states per unit area. And in 3 dimensions is like density of states per unit volume. So those are the 3 things we have. So we have an expression for conductivity, an expression for the ballistic conductance, and you can express the conductivity in terms of the ballistic conductance times the mean free path. These are the main results that you can look back, I believe it's module 1.5, where these expressions were obtained finally from the discussions in week 1. Now, in all of this discussion, as you can see, the density of states, I said, is kind of a given, like you know it from somewhere. And as I've mentioned before, usually the way you know it is from experiments where people do all kinds of like photo emission experiments and optical absorption experiments to get an idea of what these states are. And there are models that people use, which we didn't discuss at all in week 1. We said that, well, let's say we are given a density of states. Question is, what is the current flow? What is the conductance? And we obtained these expressions. Now, our objective this week is to introduce what you might call the simplest model for this density of states. And this is the model that will more or less be what we'll be using for this course. In other words, like there's a second course, as you know, another 5-week course where we go into more detail into the quantum models. But for this course, the basic model we'll be using is what I'll be discussing this week. See? Okay. So the model we'll be using is based on an important observation that dates back to the early days of solid-state physics. That is, that you see, a solid is a rather complicated object. And you might say that, well, an electron moving through the solid, must be a very complex affair. And that's indeed true. But one of the important insights that people got is very early in this, like back in the 30s and 40s, is that electrons moving through a solid behave almost as if they're moving in vacuum, but with a somewhat different mass or a different energy momentum relationship. So let me explain what I mean by that a little more. See, when you have electrons in vacuum, as you know, usually you'd write the energy, electrons just have this kinetic energy which you'd write as half mv square, usually. Or actually more generally, and that's the form I'll be using, that instead of half mv square, we'll use this p square over 2m, where usually, yes, with this p stands for momentum, that is mv. So here, of course, those two are equal. You could show easily that if p is equal to mv, those two are really the same thing. But in general, as we'll discuss, there can be more general energy momentum relations where this one may not be quite right, but this still is. So this is the one that we'll be working with. And usually people write E equals, say, p squared over 2m. And this is in vacuum, where this m then would be what we would call the free electron mass. And one of the very important insights in solid-state physics was that even in complicated solids, let's say like silicon, gallium arsenide, where electrons are moving through this complicated object, it behaves in the energy range of interest as if there's an energy momentum relation like this, but with a somewhat different mass, which people call the effective mass. And one might add a potential energy to it, a constant, EC. So this would describe electrons in many of the common semiconductors. But actually, energy momentum relations could be more complicated than that, because these days, for example, one of the more very popular materials on which there's a lot of work, both basic and applied, is graphene. And in graphene, E is actually linear with momentum. So it is there as if there's a constant times P. So in that case, you cannot quite visualize it as in terms of a mass. But the point is there is this energy momentum relation. It's well known. Now, we'll use this energy momentum relation as a starting point. So we'll say that, well, from various sources, experiments, theory, we know that in this material, we have a certain energy momentum relation, which could be this or this. And the question is, how do I obtain the density of states from a knowledge of this energy momentum relation? That's basically what we'll be talking about this week. Now, the way it works is, the way we'll do this is, we'll first define something that we'll call, let me name it, N of P. This function, what it stands for is the total number of states that you have whose momentum happens to be less than P. So let's think of a two-dimensional conductor, say. Just to be simple. So let's say I've got a two-dimensional conductor. So momentum can have an X component, and momentum could have a Y component. And if I draw a circle like this, that tells you the magnitude of the momentum. And momentum minimum, it could be 0, and then it could be something more than that. And this N of P tells you how many electronic states are available up to this radius. Now, this requires some discussion because you first have to argue that how are these states located? And that is a discussion we'll go into in the next module. But one thing you can expect without too much thinking is that if you're talking about a two-dimensional conductor, then this function n of p should depend on p squared. Why? Because if it's two dimensions, then you see the area of this circle is pi times p squared. So this should be, so the area available is proportional to p squared. So if you assume that the states are uniformly distributed in here, then the total number of states you have should be proportional to p squared. Of course, exactly what constant goes in front, that's what we'll do in the next module. So for the moment, we just note that n of p is proportional to p squared if it's two dimensions. It is, what if it is three dimensions? Well, then I should be looking at the volume of a cube. And that would then be p cubed. Or if it's one dimension, then we're just looking at a line. So it's just proportional to p. So in general, I could write n of p is proportional to p to the power d, d being the number of dimensions we are interested in. Okay. So first step then, in terms of finding density of states, is to write down this function, which, as I said, without going into much detail, we can see it should be proportional to p to the power d. Exactly what constant is in front, that's what we'll talk a little more in the next module. Now, but let's just talk about, well, even if we had this, what would we do with it? Well, the procedure is that we have n of p. Next step is we know the energy momentum relation from somewhere. So if it's graphene, it's this one. If it's silicon, it looks like this. So these are all different energy momentum relations. And what we'll do is combine n of p with this E of p. So in general, we have some energy momentum relation. So we can combine those two things to obtain a n of E. Let me take this off. So you can combine those two to obtain n of E. So what that tells you is, how many states do we have up to a given energy E? Okay. Now, what we want is this density of states. That is, how many states are available in a given range of energies. So again, let me draw this picture that I just took off. That is Px, Py. So you look at the total number of states inside this circle, that's n of p, and the p, of course, translates to a particular value of the energy, so that gives you n of E. Now, what is the density of states? Well, what you want to know is, if I increase the energy a little bit, like so, how many extra states do I get? Well, the way to think of it is, find n of E, find n of E plus dE. So this is the extra energy. And n of E is what's inside. And then if you divide it by the energy range, that will tell you the density of states per unit energy right there. So it is n of E plus dE minus n of E divided by this delta E. And this, as you'll note, is basically the derivative of n. So density of states, so my basic point is that the density of states then is given by dN dE. So that's the overall procedure then. If you are trying to write down the density of states, first question, what's the energy momentum relation? Next, write down this number of states as a function of momentum, and this is what I'll be discussing next in the next module in detail. Once you have n of p, you can turn it into n of e, and then if you take its derivative, that's what will give you the density of states. That's the d of e. That's it. And in the homework problems, we have a couple of different energy momentum relation for which I ask you to find the density of states using this procedure, and that should give you some practice as to how it works. And you can look at the video tutorial where I'll work out those examples. Okay. Now, right now, I just want to finish up this module with a short demonstration of a particular relation that should hold in general, irrespective of the energy momentum relation we use. And let me explain. So that relation, let me first state it. The relation looks something like this, that the density of states times the velocity at a given energy times the momentum should be equal to n. N is this number of states times the dimensions. So this is a general relation that should hold irrespective of the energy momentum relations. Although, depending on the energy momentum relation, you might get a different density of states, velocities would be different, etc. But this particular relation should hold in general, and this is sometimes useful. And for this homework problem, what I ask you to do is, for a specific energy momentum relation, actually calculate d and show that this relation indeed holds. And again, you can look at the tutorial to see how that's done. But right now, I just wanted to explain where that relation comes from. And it's based on this idea that n of p is actually p to the power the number of dimensions. Because what we can do then is, we could write as, so density of states, as we discussed, is derivative of n with respect to e. So what I could do is write this as dn dp times dp de. Okay. Now, one general relation that will be useful will come up later also, and that is that the definition of velocity is de dp. Again, you can check this works easily if you have if E is p square over 2m. That is the usual case. But regardless of what energy momentum relation we have, it could be a complicated energy momentum relation, the definition of velocity in general is actually this de dp. It's the rate of change of energy with momentum. And so this quantity is like 1 over v. Now, the point point to note is that as long as n has this form, p to the power d, we can write dn dp as d times p to the power d minus 1. So what that means is, again, I guess this is proportional, so let's say there is some constant here, a. So here also I'll put some constant a. A is just some constant we don't need to know. Now if I multiply both sides with p, we'll get d times a p to the power d, and that again is n. So the bottom line is that p times dn dp is equal to d times n. Now if I combine these two relations, then you'll get the relation that I stated over there. And let me just go through that quickly. Because this is 1 over V, you can see that d times V is equal to dN dP. And now, if I just multiply both sides with P, I'll put a P there and a P here. And then the point is P times dN dP is actually number of dimensions times N. So this is equal to d times N. And that's the basic relation that I stated earlier. So this is a relation that, again, I didn't make use of any particular energy momentum relation. So it holds in general, regardless of the details. And it's often a useful relation that we'll be making use of later down in this week. But what we'll now go on to in the next module is, I'll try to explain how you obtain that constant, that is, this N of P. Because once you have the number of states for a given momentum, this function, we can then, as I discussed, take any energy momentum relation and turn it into a density of states. And that's basically the concept we are trying to discuss this week.